Welcome to Podcastle's AI Voice Hub, the world's biggest library of lifelike AI voices. Choose from 1,000 plus voices and turn text to speech in a matter of seconds. Enter your own text or just hit the play button to hear how it sounds.
Imagine, if you will, that somewhere in the boundless reaches of space and time, there exists another version of yourself. This other, you might be making slightly different choices, living in a world where history unfolded along alternate paths. Perhaps in that universe, the dinosaurs never went extinct, or perhaps the fundamental constants of physics are subtly different, creating entirely alien forms of matter and energy. This is not merely the stuff of science fiction. These possibilities emerge from the deepest investigations into the nature of reality itself, arising from our most sophisticated theories of quantum mechanics, cosmology, and the fundamental structure of TOS. Space and time. The story of parallel universes is a story that begins in the ancient halls of philosophical inquiry and extends to the cutting edge of modern theoretical physics. The philosophical origins long before the advent of modern science, human minds grappled with questions about the nature of existence and reality. In ancient Greece, philosophers like Democritus proposed that the universe was composed of countless atoms moving through infinite void. This atomistic worldview naturally led to questions about what might exist beyond our immediate experience. The ancient Greek philosopher Anaxagoras suggested that in an infinite universe, every possible combination of matter must occur somewhere. This early insight contained the seeds of ideas that would later flourish in modern cosmology. If space extends infinitely in all directions, and matter is distributed throughout it, then eventually, given enough distance, every possible arrangement of atoms must repeat itself. This philosophical intuition found expression in various forms throughout history. The Roman poet Lucretius, following the atomistic tradition, wrote of countless worlds scattered throughout infinite space, each containing its own unique combination of circumstances and life forms. He described these worlds as arising naturally from the random collision and combination of atoms, suggesting that our universe was just one of many possible arrangements of matter. In medieval Islamic philosophy, thinkers like Al-Ghazali explored the concept of multiple worlds, though often in a theological context. The idea that God might have created multiple universes, each perfect in its own way, provided a framework for understanding divine omnipotence and the richness of creation itself. The Renaissance brought renewed interest in these questions. Giordano Bruno, the Italian philosopher and astronomer, boldly proposed that the universe contained infinite worlds, each populated with its own forms of life. His vision extended beyond mere philosophical speculation, incorporating astronomical observations and mathematical reasoning. For these ideas, among others, Bruno paid the ultimate price, burned at the stake for heresy in 1600. Bruno's vision was remarkably prescient. He imagined that each star might be a sun like our own, surrounded by planets that could harbor life. This multiplicity of worlds, he argued, reflected the infinite creativity and power of the divine. In Bruno's universe, no two worlds were exactly alike, yet all were expressions of the same underlying principles that governed reality. The German philosopher Gottfried Leibniz introduced another crucial concept that would later influence theories of parallel universes. In his philosophical system, Leibniz proposed that our world is the best of all possible worlds, but he acknowledged that other possible worlds existed in the realm of divine knowledge. These alternate realities, while not actualized, remained coherent possibilities that helped define the nature of the world we inhabit. Leibniz's notion of possible worlds provided a framework for thinking about modal logic and the nature of necessity and possibility. If we can conceive of alternative ways the world might have been, what is the status of these unrealized possibilities? Do they exist in some sense, or are they merely mental constructs? The Enlightenment philosopher David Hume pushed these questions further, arguing that our knowledge of the world is fundamentally limited by our experience. If we can only know what we directly observe, how can we be certain that our universe is the only one that exists? Hume's skepticism opened the door to considering radical alternatives to our assumed picture of reality. As the 18th and 19th centuries progressed, Advances in mathematics and physics began to provide new tools for exploring these ancient questions. The development of non-Euclidean geometries suggested that the fundamental structure of space itself might be more flexible than previously imagined. If different geometric principles could govern space, might there be regions of reality where these alternative geometries actually applied? The philosopher Immanuel Kant grappled with questions about the nature of space and time, ultimately arguing that these were not features of reality itself, but rather the necessary conditions under which human minds organize experience. This Kantian insight raised profound questions about the relationship between the world as we experience it and the world as it truly is. If space and time are subjective features of human cognition, what might reality look like from a perspective that transcends these limitations? By the late 19th century, these philosophical speculations were beginning to encounter new challenges and opportunities arising from developments in physics. The discovery of electromagnetic fields and the development of field theory suggested that space itself might be filled with invisible influences and energies. The stage was being set for revolutionary developments that would transform speculative philosophy into scientific theory. The quantum revolution, the dawn of the 20th century, brought with it a series of discoveries that would fundamentally transform our understanding of reality. The advent of quantum mechanics revealed a world far stranger than anything previously imagined, where particles existed in multiple states simultaneously, where the act of observation seemed to influence physical reality, and where the very foundations of classical determinism crumbled under the weight of experimental evidence. The story begins with Max Planck's reluctant introduction of the quantum of action in 1900. Planck was attempting to solve a seemingly mundane problem in thermodynamics, explaining the spectrum of light emitted by heated objects. His solution required assuming that energy could only be emitted or absorbed in discrete packets, or quanta. This assumption was so radical that Planck himself initially resisted its implications. Albert Einstein extended Planck's insight in his explanation of the photoelectric effect, demonstrating that light itself comes in discrete packets, later called photons. This discovery earned Einstein the Nobel Prize and established the particle nature of electromagnetic radiation. Yet even Einstein would later struggle with the broader implications of quantum theory, famously declaring that God does not play dice with the universe. As quantum mechanics developed through the work of Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others, it became clear that the atomic world operated according to principles that defied classical intuition. Particles did not have definite positions and velocities simultaneously. Instead, they existed in states of superposition, where all possible values of their properties coexisted until the moment of measurement. Heisenberg's uncertainty principle revealed that this indefiniteness was not merely a limitation of our measuring instruments, but a fundamental feature of reality itself. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This principle suggested that reality at the quantum scale is inherently probabilistic rather than deterministic. Schrödinger's wave equation provided a mathematical framework for describing quantum systems, but its interpretation raised profound puzzles. The wave function seemed to describe a particle's probability of being found in various states, but what happened to all the other possibilities when a measurement was made? The standard Copenhagen interpretation, developed primarily by Bohr and Heisenberg, suggested that the wave function collapsed upon measurement, randomly selecting one outcome from the many possibilities. This interpretation, while mathematically successful, troubled many physicists with its apparent arbitrariness. Why should the act of measurement have such a special role in determining physical reality? What constituted a measurement, and where exactly did the quantum world end and the classical world begin? These questions became more pressing as quantum mechanics was applied to larger and more complex systems. If a single particle could exist in multiple states simultaneously, what about systems composed of many particles? Could larger objects also exist in quantum superposition? And if so, why don't we observe such effects in everyday life? The divide between quantum and classical behavior seems to require some kind of boundary or threshold, but no fundamental principle suggested where such a boundary might lie. This puzzle would eventually lead to one of the most radical proposals in the history of physics: the many-worlds interpretation of quantum mechanics. Meanwhile, other developments in early 20th century physics were opening up new perspectives on the nature of space and time. Einstein's special theory of relativity revealed that space and time were intimately connected, forming a unified space-time continuum. His general theory of relativity went further, showing that matter and energy could curve space-time, creating the phenomena we experience as gravity. These discoveries suggested that the universe was far more dynamic and flexible than previously imagined. If massive objects could bend space-time, might there be regions where space-time curved back on itself, creating closed loops or connections to distant regions? Could there be portions of space-time that remained forever hidden from our observation? The combination of quantum mechanics and relativity theory opened up possibilities that neither theory alone had suggested. If space-time could have complex topological structures, and if quantum mechanics allowed for multiple simultaneous realities, then perhaps the universe was far stranger and more richly populated than anyone had previously imagined. The many-worlds interpretation in 1957, a young physics graduate student at Princeton University named Hugh Everett III, proposed a radical solution to the measurement problem in quantum mechanics. Rather than assuming that the wave function collapsed when a measurement was made, Everett suggested that all possible outcomes of a quantum measurement actually occur, each in its own separate branch of reality. This proposal, which came to be known as the many-worlds interpretation, was so radical that it initially received little attention from the physics community. Everett's thesis advisor, John Wheeler, was intrigued but cautious, and the broader physics establishment was largely dismissive. The idea seemed to violate principles of scientific economy and common sense. How could every quantum event spawn entire new universes? Yet Everett's mathematics was impeccable. He showed that if the wave function never collapsed, but instead continued to evolve according to Schrödinger's equation, then the result would be a constantly branching tree of realities. Each possible outcome of each quantum measurement would be realized somewhere in this vast structure, and observers would find themselves following specific paths through the branching possibilities. From the perspective of any individual observer, the experience would be exactly what the Copenhagen interpretation predicted. A measurement would yield a single, apparently random result, with probabilities matching those calculated from the wave function. The crucial difference was that all the other possible results would also occur, but in parallel worlds that remained forever inaccessible to the original observer. This interpretation elegantly solved several persistent puzzles in quantum mechanics. It eliminated the arbitrary distinction between quantum and classical systems, since everything evolved according to the same fundamental equation. It removed the need for wave function collapse, which had always seemed like an ad hoc addition to the theory. And it provided a completely deterministic account of quantum phenomena, restoring a kind of causality that the Copenhagen interpretation had abandoned. The branching structure that Everett described was not a branching of space or time in any conventional sense. Instead, it was a branching of what physicists call configuration space, an abstract mathematical arena that encompasses all possible states of a quantum system. When a quantum measurement occurs, the universe does not split into separate spatial regions. Rather, the universal wave function evolves to include multiple components, each corresponding to a different measurement outcome. From a mathematical standpoint, these components are perfectly real and equally valid descriptions of reality. There is no physical reason to privilege one component over another. Each branch contains observers who experience a consistent history and who have no direct access to the other branches. The apparent randomness of quantum measurement results from the fact that any individual observer can only experience one branch of the universal wave function. This picture has profound implications for the nature of personal identity and experience. If every quantum event creates multiple versions of yourself, which one is the real you? Everett argued that this question was meaningless. Each branch contains a version of you that is equally real and equally entitled to consider itself the original. The continuity of personal identity is maintained within each branch, even as it proliferates across branches. The many-worlds interpretation also provides a new perspective on probability and causation. In a branching universe, every possible outcome of every event actually occurs somewhere. The events we consider improbable are not prevented from happening, they simply occur in a smaller fraction of the branches. This suggests a kind of democratic universe where all possibilities are given their due, weighted according to their quantum mechanical probabilities. As the interpretation gained attention, it attracted both enthusiastic supporters and fierce critics. Supporters appreciated its mathematical elegance and its resolution of quantum paradoxes. Critics objected to its apparent violation of Occam's razor, arguing that a theory that postulated countless unobservable universes could hardly be considered simple or economical. The debate over the many worlds interpretation continues to this day, with physicists divided on its merits. Some view it as the most natural and consistent interpretation of quantum mechanics, while others consider it an extravagant metaphysical speculation. Regardless of one's position on its truth, the interpretation has had an enormous impact on how physicists think about quantum mechanics and the nature of reality. The many worlds interpretation also opened up new avenues for research and speculation. If parallel worlds exist at the quantum level, might there be other mechanisms that could generate parallel universes on larger scales? Could the same branching processes that operate in microscopic systems also apply to cosmological phenomena? Quantum mechanics and superposition to fully appreciate the revolutionary implications of the many worlds interpretation. We must delve deeper into the strange world of quantum superposition and the experimental evidence that supports these counterintuitive ideas. The principle of superposition lies at the heart of quantum mechanics, asserting that quantum systems can exist in combinations of multiple states simultaneously. Consider the quantum property called spin, which can be measured along any chosen axis. For certain particles, a measurement of spin can yield only two possible results, up or down, relative to the measurement direction. Classical intuition suggests that the particle must have a definite spin direction prior to measurement, even if we don't know what it is. Quantum mechanics, however, reveals a far stranger reality. Before measurement, a quantum particle exists in a superposition of both spin up and spin down. This is not simply a statement about our ignorance of the particle's true state. Rather, the particle genuinely possesses both properties simultaneously in a way that defies classical description. The mathematics of quantum mechanics describes this superposition precisely, assigning probability amplitudes to each possible state. These probability amplitudes are complex numbers that encode not only the likelihood of measuring each state, but also the quantum mechanical phases that determine how different states can interfere with one another. This interference is the key signature of superposition, producing effects that cannot be explained by any classical mixture of definite states. The double-slit experiment provides perhaps the most famous demonstration of quantum superposition. When individual particles, such as electrons or photons, are sent through a barrier containing two closely spaced slits, they create an interference pattern on a detection screen behind the barrier. This pattern is characteristic of waves, suggesting that each particle somehow travels through both slits simultaneously. When physicists attempt to determine which slit each particle passes through by placing detectors near the slits, the interference pattern disappears. The particles now behave like classical projectiles, passing through one slit or the other, but never both. This dramatic change in behavior, triggered simply by the presence of measuring apparatus, illustrates the central mystery of quantum measurement. The transition from quantum superposition to classical definiteness has been studied in increasingly sophisticated experiments. Physicists have observed superposition effects in systems of growing complexity, from individual atoms to small molecules to microscopic mechanical oscillators. Each advance in experimental technique pushes the boundary between quantum and classical behavior to larger scales. One of the most striking demonstrations involved an experiment where a tiny mechanical resonator, visible under an optical microscope, was placed in a quantum superposition of two different vibrational paths, states. The resonator was simultaneously vibrating and not vibrating, existing in a macroscopic quantum superposition that bridged the gap between the microscopic quantum world and everyday classical bus experience. These experiments reveal that the principles of quantum superposition are not limited to the atomic scale, but extend to larger systems when they are sufficiently isolated from their environment. The process of decoherence, whereby quantum superpositions are destroyed through interaction with the surrounding environment, provides a natural explanation for why we don't observe quantum effects in everyday life. Decoherence occurs when a quantum system becomes entangled with its environment through countless microscopic interactions. These interactions effectively measure the system's properties, causing the superposition to evolve into a classical mixture of definite states. The process is extremely rapid for macroscopic objects, occurring in tiny fractions of a second and making quantum superposition practically unobservable in normal circumstances. Yet decoherence does not solve the measurement problem in quantum mechanics. While it explains why superpositions become unobservable, it does not explain why we observe specific outcomes rather than others. The many-worlds interpretation addresses this puzzle by proposing that all possible outcomes occur, with decoherence serving to separate the different branches rather than select among them. Recent developments in quantum technology have allowed physicists to observe and control decoherence with unprecedented precision. Quantum computers rely on maintaining coherent superpositions long enough to perform useful calculations, requiring extraordinary efforts to isolate quantum systems from their environments. These technological advances have provided new insights into the fundamental nature of quantum mechanics and the transition between quantum and classical behavior. The study of quantum superposition has also revealed deep connections between information theory and physics. The amount of information required to fully describe the quantum superposition grows exponentially with the number of particles involved, suggesting that classical computers cannot efficiently simulate large ensemble quantum systems. This insight has led to the development of quantum computing and quantum simulation, technologies that exploit the vast computational resources implicit in quantum superposition. The measurement problem in quantum mechanics stands as one of the most profound and persistent puzzles in all of physics. It arises from the apparent contradiction between the smooth, deterministic evolution of quantum systems described by the Schrödinger equation and the sudden, random outcomes observed when these systems are measured. According to the fundamental equations of quantum mechanics, physical systems evolve in a completely predictable way. The wave function that describes a quantum system changes over time according to precise mathematical rules, with no randomness or discontinuity. Yet when we perform measurements on these systems, we observe definite, apparently random outcomes that seem to emerge from nowhere. This puzzle becomes particularly acute when we consider the process of measurement itself. What distinguishes a measurement from any other physical interaction? If everything in the universe is governed by quantum mechanics, then measuring devices should themselves be quantum systems, evolving according to the same deterministic equations. How then can they produce the definite, classical outcomes that we observe? The standard Copenhagen interpretation addresses this problem by introducing a fundamental distinction between quantum systems and classical measuring apparatus. According to this view, the act of measurement causes the wave function to collapse, randomly selecting one of the possible outcomes with probabilities determined by the wave function's magnitude. This collapse process is postulated as a basic feature of nature, not derivable from the underlying quantum equations. While the Copenhagen interpretation provides a practical recipe for calculating experimental results, it leaves many conceptual questions unanswered. What exactly constitutes a measurement? Where is the boundary between quantum systems and classical apparatus? Why should consciousness or observation play a special role in determining physical reality? These questions become even more perplexing when we consider Schrödinger's famous thought experiment involving a cat placed in a sealed box with a quantum-triggered poison mechanism. If quantum mechanics applies to the entire system, including the cat, then before the box is opened, the cat should exist in a superposition of alive and dead states. Only when the box is opened and the cat is observed should the wave function collapse to yield a definite outcome. Most physicists find this conclusion absurd, yet it follows logically from the standard interpretation of quantum mechanics. The cat paradox illustrates the difficulty of reconciling quantum principles with everyday experience, and highlights the arbitrary nature of the classical quantum boundary in the Copenhagen interpretation. Alternative interpretations of quantum mechanics have been developed to address these conceptual problems. The many-worlds interpretation, as we have seen, eliminates wave function collapse entirely, arguing that all possible measurement outcomes occur in parallel branches of reality. This approach resolves the arbitrariness of the measurement process, but at the cost of accepting an enormous ontology of unobservable parallel worlds. Hidden variable theories, most notably the de Broglie-Bohm theory, propose that quantum randomness arises from our ignorance of underlying deterministic variables that guide the evolution of quantum systems. These theories restore a classical picture of reality at the cost of introducing non-local influences that propagate faster than light. Objective collapse theories modify the Schrödinger equation itself, adding random terms that cause wave functions to collapse spontaneously after reaching a certain threshold of macroscopic complexity. These theories make definite predictions about when and how collapse occurs, but they require abandoning the fundamental linearity of quantum mechanics. The measurement problem has practical implications beyond its philosophical interest. In quantum computing and quantum information processing, understanding the precise boundary between quantum and classical behavior is essential for designing systems that can maintain quantum coherence long enough to perform useful calculations. Recent experiments have probed the measurement process with unprecedented precision, revealing subtle features that were previously hidden. These studies show that the transition from quantum to classical behavior is more gradual and complex than early interpretations suggested, involving intricate patterns of entanglement between systems and their environments. The development of quantum error correction and quantum control techniques has also provided new insights into the nature of measurement and decoherence. By actively protecting quantum systems from environmental disturbance, physicists have been able to maintain superposition states for extended periods and observe the gradual onset of classical behavior. Despite decades of research and debate, the measurement problem remains unresolved. Different interpretations of quantum mechanics offer different solutions, but none has achieved universal acceptance among physicists. This ongoing uncertainty reflects the profound conceptual challenges posed by quantum mechanics and the difficulty of reconciling its mathematical formalism with our intuitive understanding of reality. The measurement problem also connects to broader questions in philosophy of science about the nature of scientific explanation and the relationship between theory and observation. Some philosophers argue that the problem reflects fundamental limitations in our conceptual frameworks rather than genuine features of physical reality. Thought experiments and paradoxes. The development of quantum mechanics has been accompanied by a series of ingenious thought experiments designed to illuminate the theory's conceptual foundations and explore its philosophical implications. These mental exercises have played a crucial role in shaping our understanding of quantum phenomena and continue to inspire new research directions. Perhaps the most famous of these is Schrödinger's cat, introduced by Erwin Schrödinger in 1935 as a critique of the Copenhagen interpretation. Schrödinger was troubled by the idea that quantum superposition could extend to macroscopic objects, and he devised his thought experiment to highlight what he saw as an absurd consequence of this view. In Schrödinger's scenario, a cat is placed in a sealed box along with a Geiger counter, a small amount of radioactive material, a hammer, and a flask of poison. The radioactive material has a 50% chance of decaying within an hour. If decay occurs, the Geiger counter detects it and triggers a mechanism that breaks the poison flask, killing the cat. If no decay occurs, the cat remains alive. From a quantum mechanical perspective, before the box is opened, the radioactive material exists in a superposition of decayed and undecayed states. If this superposition extends to the entire system, then the cat itself must exist in a superposition of alive and dead states. Only when the box is opened does this superposition collapse, randomly determining the cat's fate. Schrödinger found this conclusion ridiculous, arguing that it demonstrated the inadequacy of applying quantum mechanics to macroscopic systems. However, his thought experiment had the opposite effect of what he intended. Rather than discrediting quantum mechanics, it focused attention on the measurement problem and inspired new interpretations of the theory. The many worlds interpretation provides a straightforward resolution to the cat paradox. In this view, both outcomes occur, but in separate branches of reality. In one branch, the radioactive material decays and the cat dies. In another branch, no decay occurs and the cat lives. Observers in each branch experience only their branch's outcome, with no direct access to the parallel reality. Another influential thought experiment was proposed by Einstein, Podolsky, and Rosen in 1935. The EPR paradox, as it came to be known, challenged the completeness of quantum mechanics by highlighting the phenomenon of quantum entanglement. The three physicists described a system of two particles that interact briefly and then separate to distant locations. According to quantum mechanics, measurements performed on one particle can instantly determine the properties of the other particle, regardless of the distance between them. Einstein and his colleagues argued that this spooky action at a distance violated the principle of locality, which states that objects can only be directly influenced by their immediate surroundings. The EPR paradox suggested that quantum mechanics must be incomplete, missing some crucial information about the system's true state. Einstein believed that hidden variables must exist that predetermine the outcomes of all measurements, eliminating the need for instantaneous non-local influences. This debate remained largely philosophical until 1964, when physicist John Stuart Bell derived a mathematical theorem that could distinguish between quantum mechanics and hidden variable theories. Bell's theorem shows that any local hidden variable theory must satisfy certain inequalities when applied to entangled systems. Quantum mechanics, however, predicts violations of these inequalities under specific experimental conditions. Subsequent experiments, beginning with Alain Aspect's pioneering work in the 1980s, have repeatedly confirmed quantum mechanical predictions and ruled out local hidden variable theories. These results demonstrate that quantum entanglement is indeed a genuine feature of nature, not merely a consequence of incomplete knowledge. The confirmation of Bell's theorem has profound implications for our understanding of reality. It suggests that the world is fundamentally non-local, with distant events capable of instantaneous correlation through quantum entanglement. This non-locality does not permit faster-than-light communication, but it does reveal deep connections between separated parts of the universe. Wigner's Friend, another influential thought experiment, explores the role of consciousness in quantum measurement. Eugene Wigner imagined a scenario where his friend performs a quantum measurement inside a sealed laboratory. From Wigner's external perspective, the entire laboratory, including his friend, exists in quantum superposition until Wigner opens the laboratory and observes the result. This thought experiment raises questions about the subjective nature of wave function collapse. Does the collapse occur when Wigner's friend makes the measurement, or only when Wigner himself observes the outcome? If consciousness plays a role in determining physical reality, whose consciousness is fundamental? Recent developments have extended Wigner's thought experiment to even more complex scenarios involving networks of observers. These extended versions reveal subtle inconsistencies in the idea that consciousness causes wave function collapse, lending support to interpretations that eliminate collapse entirely. The quantum Zeno effect, inspired by the ancient Greek paradox of motion, demonstrates how frequent measurements can freeze the evolution of a quantum system. Just as Zeno argued that an arrow in flight never moves because it is always at rest at each instant, frequent quantum measurements can prevent a system from evolving by repeatedly collapsing its wave function. This effect has been observed experimentally and has practical applications in quantum technology. By carefully timing measurements, physicists can protect quantum information from decoherence and control the evolution of complex quantum systems. The delayed choice experiment, proposed by John Wheeler, explores the strange temporal aspects of quantum measurement. In this thought experiment, the decision of whether to measure particle-like or wave-like properties is made after the particle has already passed through the experimental apparatus. Remarkably, this delayed choice still determines the nature of the particle's behavior throughout the entire experiment. These thought experiments illustrate the conceptual richness of quantum mechanics and its departure from classical intuition. They have guided the development of new interpretations and continue to inspire experimental tests of quantum foundations. More broadly, they demonstrate the power of careful conceptual analysis in revealing the deep structure of physical reality. Cosmological inflation and bubble universes as our understanding of quantum mechanics deepened throughout the 20th century. Parallel developments in cosmology were revealing the universe to be far stranger and more dynamic than previously imagined. The discovery of the cosmic expansion, the cosmic microwave background radiation, and the synthesis of light elements in the early universe established the Big Bang theory as the standard model of cosmology. Yet the Big Bang theory, while successful in explaining many observed features of the universe, also raised new puzzles. Why is the universe so remarkably uniform in temperature across vast regions that have never been in causal contact? Why is the geometry of space so close to perfectly flat? Why are certain relics predicted by particle physics theories, such as magnetic monopoles, nowhere to be found? These problems found their resolution in the theory of cosmic inflation, developed primarily by Alan Guth, André Linde, and others in the early 1980s. Inflation proposes that the universe underwent a period of exponential expansion in its earliest moments, driven by the energy stored in a special quantum field called the inflaton. During the inflationary epoch, the universe expanded by an enormous factor in a tiny fraction of a second. This rapid expansion stretched out any initial irregularities in curvature, leaving behind a universe that appears uniform and flat on large scales. The quantum fluctuations in the inflaton field were amplified by the expansion, providing the seeds for the formation of galaxies and large-scale structure. Inflation not only solved the puzzles of the standard Big Bang model, but also made specific predictions that could be tested observationally. The theory predicted a particular pattern of temperature fluctuations in the cosmic microwave background radiation, which were subsequently observed by satellite missions such as COBE, WMAP, and Planck. However, inflation also opened up a remarkable new possibility for the existence of parallel universes. In most inflationary models, the process that drives inflation does not end everywhere at the same time. While inflation ends in some regions, allowing normal Big Bang evolution to proceed, it continues in other regions, creating an endless process of expansion and universe formation. This scenario, known as eternal inflation, suggests that our observable universe is just one bubble in a vast inflating space filled with countless other bubble universes. Each bubble represents a region where inflation has ended and normal physics takes over. But the space between bubbles continues to expand exponentially. The bubble universes created by eternal inflation could have very different properties from our own. The fundamental constants of physics, the number of spatial dimensions, and even the basic laws of nature might vary from bubble to bubble. This variation could arise from the different ways that quantum fields settle into their lowest energy states as each bubble universe forms. In some models, the landscape of possible vacuum states is incredibly rich, with perhaps 500 different possibilities. Each bubble universe would randomly select one of these vacuum states, leading to an enormous diversity of physical conditions across the multiverse. Only a tiny fraction of these bubbles would have conditions suitable for the formation of stars, planets, and life as we know it. This scenario provides a new perspective on the apparent fine-tuning of physical constants in our universe. Many of the parameters that govern physics appear to be precisely adjusted to allow for the existence of complex chemistry and biology. If these parameters were even slightly different, stars might not form, atoms might not be stable, or the universe might collapse before life could evolve. In a multiverse containing bubble universes with all possible parameter values, this fine-tuning becomes less mysterious. We necessarily find ourselves in a bubble universe with parameters compatible with our existence, not because these parameters were specially chosen, but because we could not exist in bubbles with different parameters. This application of the anthropic principle suggests that apparent design in the universe might simply reflect observational selection effects. The eternal inflation scenario also connects to quantum mechanics through the role of quantum fluctuations in driving the inflationary process. The quantum vacuum contains temporary fluctuations in energy that can, under the right conditions, trigger new episodes of inflation. This quantum mechanical input ensures that the process of bubble universe creation continues indefinitely. Recent observations of the cosmic microwave background have provided increasingly stringent tests of inflationary models. The detected patterns of temperature fluctuations match the predictions of inflation with remarkable precision, lending strong support to the basic inflationary picture. However, these observations have also ruled out some of the simpler inflationary models and pointed toward more complex scenarios. The study of cosmic inflation has also revealed deep connections between cosmology and fundamental physics. Inflationary models often invoke physics beyond the standard model of particle physics, including extra dimensions, supersymmetry, and string theory. These connections suggest that cosmological observations might provide crucial clues about the fundamental nature of space, time, and matter. Advanced gravitational wave detectors may eventually be able to observe the signatures of cosmic inflation directly. Inflation is predicted to produce gravitational waves that would leave distinctive patterns in the polarization of the cosmic microwave background radiation. The detection of these primordial gravitational waves would provide smoking gun evidence for inflation and offer new insights into the physics of the very early universe. The bubble universe scenario raises profound questions about the nature of scientific explanation and prediction. If our universe is just one of infinitely many with randomly varying properties, can we ever hope to understand why the laws of physics take their observed forms? Some physicists argue that the multiverse hypothesis is untestable and therefore unscientific, while others contend that it is a natural consequence of our best theories and should be taken seriously. String theory and extra dimensions, the quest to unify all fundamental forces of nature, has led physicists to one of the most ambitious and controversial theories in modern physics, string theory. This framework proposes that the most basic constituents of reality are not point-like particles, but rather tiny vibrating strings existing in a higher dimensional spacetime. String theory emerged from attempts to understand the strong nuclear force in the 1960s and 1970s, but it soon became apparent that the theory had far grander ambitions. The mathematical structure of string theory naturally incorporates gravity along with the other fundamental forces, suggesting that it might provide the long-sought theory of quantum gravity. In string theory, the familiar particles of the standard model electrons, quarks, photons, and the rest arise as different vibrational modes of these fundamental strings. Just as a violin string can vibrate at different frequencies to produce different musical notes, the strings of string theory can vibrate in different patterns to produce different particles with distinct masses and properties. One of the most striking features of string theory is its requirement for extra spatial dimensions beyond the three we observe in everyday life. Depending on the specific version of the theory, string theory requires either 6 or 7 additional spatial dimensions, bringing the total to 9 or 10 spatial dimensions plus 1 time dimension. These extra dimensions must be compactified or curled up on scales so small that they remain hidden from direct observation. The geometry of this compactification determines many of the observed properties of particles and forces, including the masses of particles and the strengths of their interactions. The landscape of possible compactifications in string theory is extraordinarily vast. Mathematicians have identified thousands of different ways to curl up the extra dimensions, each corresponding to a different possible physics for our four-dimensional world. Some estimates suggest that the total number of possible compactifications could be as large as 10^500, and others so large that it dwarfs the number of atoms in the observable universe. This vast landscape of possibilities connects string theory to the multiverse concept in a profound way. If string theory is correct, and if different regions of a larger space can realize different compactifications, then we might live in a multiverse where the laws of physics vary from region to region according to the local geometry of the extra dimensions. In this string theory multiverse, our observable universe would correspond to a region where the extra dimensions are compactified in one particular way. Other regions might have different compactifications, leading to different particle masses, force strengths, and even different numbers of observable spatial dimensions. The process of compactification in string theory involves complex geometric structures known as Calabi-Yau manifolds. These higher dimensional shapes have intricate topologies that can trap strings in specific vibrational patterns. The particular Calabi-Yau manifold that characterizes our region of space determines the physics we observe. The enormity of the string landscape has led to intense debates about the predictive power of the theory. If string theory allows for 10,500 different possible physics, how can we ever hope to calculate which one applies to our universe? Critics argue that such a theory becomes unfalsifiable and therefore unscientific. Proponents of string theory respond that the vast landscape might actually be a feature rather than a bug. In combination with eternal inflation, the string landscape could provide a natural explanation for the apparent fine-tuning of physical constants. If inflation creates bubble universes with all possible string compactifications, then observers like ourselves would naturally find ourselves in regions with physics compatible with our existence. The extra dimensions of string theory also open up new possibilities for parallel universes that exist alongside our own in the higher dimensional space. While we are confined to our three-dimensional slice of space-time, other three-dimensional universes might exist on parallel slices, separated from us in the extra dimensions. This scenario, known as the brain world model, suggests that our entire universe might be a three-dimensional membrane, or brain, floating in a higher dimensional space called the bulk. Other brains might exist nearby in the extra dimensions, hosting their own versions of matter, energy, and possibly life. The gravitational force, which in string theory arises from closed strings that can move freely through all dimensions, would provide the only means of communication between parallel brains. This could explain why gravity is so much weaker than the other fundamental forces. Most of its influence might be diluted by spreading into the extra dimensions. Collisions between brains in the higher dimensional space could trigger the Big Bang events that create new universes. In some cyclic cosmological models, our universe undergoes endless cycles of expansion, contraction, and collision with a parallel brain, each cycle resetting the cosmic clock and potentially reshuffling the bar. Fundamental constants. The mathematics of string theory has also revealed deep connections between apparently different physical theories. String duality relationships show that what appears to be one physical situation from one perspective can be described as a completely different situation from another perspective. Add S/CFT correspondence, one of the most important developments in theoretical physics of the past few decades, demonstrates that a gravitational theory in a space with a particular geometry is mathematically equivalent to a quantum field theory without gravity living on the boundary of that space. This remarkable duality suggests that the interior of a space and its boundary might be different descriptions of the same physical reality. Such dualities raise profound questions about the fundamental nature of space and reality. If two apparently different descriptions can capture the same physics, which one represents the true nature of reality? Perhaps the question itself is meaningless, and we should think of these different descriptions as complementary windows into a deeper truth that transcends any single mathematical formulation. The holographic principle inspired by these string theory dualities suggests that the information content of any region of space can be encoded on its boundary. This principle implies that what we experience as three-dimensional reality might actually be a projection from information stored on a two-dimensional surface. If the holographic principle is correct, then our entire universe might be a kind of holographic projection from information encoded on a distant boundary. This possibility adds yet another layer to the multiverse concept, suggesting that what we consider to be fundamental reality might itself be an emergent phenomenon arising from more basic information theoretic processes. Recent developments in string theory have focused on understanding how spacetime itself might emerge from more fundamental quantum mechanical degrees of freedom. In these approaches, space and time are not basic features of reality, but rather collective phenomena that arise when many quantum bits of information become entangled in specific patterns. This emergence of spacetime from quantum entanglement provides a new perspective on parallel universes. Different patterns of entanglement might give rise to different spacetime geometries, potentially creating a multiverse of interconnected quantum realities. The boundaries between different universes might not be sharp divisions in space, but rather gradual transitions in the underlying pattern of quantum correlations. Quantum entanglement and non-locality quantum entanglement represents one of the most profound and counterintuitive features of quantum mechanics, creating correlations between particles that transcend the classical boundaries of space and time. When two or more particles become entangled, they form a unified quantum system that cannot be described as a collection of independent parts, no matter how far apart the particles might travel. The phenomenon of entanglement was first recognized by Schrödinger, who coined the term to describe what he considered the most important characteristic of quantum mechanics. He realized that when quantum systems interact, they can become correlated in ways that have no classical analog, creating what Einstein famously dismissed as spooky action at a distance. To understand entanglement, consider two particles that interact briefly and then separate to opposite ends of the galaxy. If these particles are entangled, measuring a property of one particle instantly determines the corresponding property of the other particle, regardless of the vast distance between them. This correlation occurs faster than light could travel between the particles, appearing to violate the fundamental principle of relativity that nothing can travel faster than light. The resolution to this apparent paradox lies in understanding what information can and cannot be transmitted through entanglement. While the correlations between entangled particles are indeed instantaneous, they cannot be used to send messages or information from one location to another. The outcomes of measurements on entangled particles appear random to any individual observer, with the correlations only becoming apparent when measurement results are compared. This limitation prevents entanglement from violating causality or enabling faster-than-light communication. However, it does not diminish the profound implications of entanglement for our understanding of reality. The existence of instantaneous correlations across arbitrary distances suggests that the universe has a fundamentally non-local character that defies classical intuitions about space and separation. Bell's theorem, proved in 1964, demonstrated that these quantum correlations are genuinely non-local and cannot be explained by any theory that assumes local hidden variables. Subsequent experiments have repeatedly confirmed Bell's predictions, establishing entanglement as a fundamental feature of nature rather than a mathematical curiosity. The verification of quantum non-locality has far-reaching implications for parallel universe theories. If particles in our universe can be instantaneously correlated across vast distances, might there also be correlations that extend across the boundaries between parallel universes? Some interpretations of quantum mechanics suggest that entanglement might indeed connect different branches of the multiverse. In the many worlds interpretation, measurement outcomes in different branches could remain correlated through quantum entanglement, even though the branches themselves become inaccessible to direct observation. This possibility raises fascinating questions about the nature of information and correlation in a multiverse. Could events in one universe influence the probabilities of events in parallel universes through entanglement connections? Might the apparent randomness of quantum measurements actually reflect the influence of unmeasurable correlations with parallel realities? Recent developments in quantum information theory have revealed that entanglement is not merely a curiosity, but a fundamental resource that enables entirely new forms of computation and communication. Quantum computers exploit entanglement to perform certain calculations exponentially faster than classical computers, while quantum cryptography uses entanglement to enable absolutely secure communication. These practical applications of entanglement have driven rapid advances in our ability to create, manipulate, and measure entangled systems. Physicists can now routinely entangle particles across hundreds of kilometers and maintain entanglement in complex multiparticle systems for extended periods. The study of many-body entanglement has revealed rich and complex structures in quantum systems composed of numerous interacting particles. These systems can exhibit different phases of entanglement, analogous to the familiar phases of matter like solid, liquid, and gas, but characterized by patterns of quantum correlation rather than classical order. Topological phases of matter represent a particularly exotic form of many-body entanglement, where the quantum correlations are protected against local disturbances by global topological properties. These phases could potentially serve as the basis for fault-tolerant quantum computers that are naturally protected against certain types of errors. The emergence of spacetime from entanglement has become an active area of research at the intersection of quantum mechanics, gravity, and cosmology. According to this perspective, the geometric properties of spacetime arise from the pattern of entanglement between microscopic quantum degrees of freedom. In this view, the smooth spacetime that we experience in everyday life is an emergent phenomenon, similar to how the smooth flow of a fluid emerges from the chaotic motion of its constituent molecules. The fundamental building blocks of reality might be quantum bits of information whose entanglement patterns give rise to the illusion of continuous space and time. This emergent view of spacetime has profound implications for parallel universe theories. If spacetime itself emerges from entanglement patterns, then different patterns might give rise to different spacetime geometries. The multiverse might consist not of separate spatial regions, but of different emergent realities arising from distinct quantum correlation structures. The holographic principle, derived from string theory and black hole physics, provides a concrete realization of this idea. It suggests that all the information in a volume of space can be encoded on its boundary, with the interior spacetime emerging from the entanglement structure of the boundary theory. Recent research has shown that entanglement can create geometric connections between distant regions of spacetime through quantum wormholes. These Einstein-Rosen bridges, while not traversable by classical matter, represent genuine geometric connections created and maintained by quantum entanglement. The discovery of quantum error correction in gravity has revealed deep connections between entanglement, spacetime geometry, and information theory. These connections suggest that the preservation of information in quantum gravity requires specific patterns of entanglement that naturally give rise to the geometric properties of spacetime. Mathematical frameworks and infinite realities, the mathematical foundations underlying theories of parallel universes, reveal structures of breathtaking complexity and beauty. These frameworks suggest that reality itself might be far richer and stranger than anything accessible to direct human experience, extending into infinite hierarchies of possibility that challenge our most basic intuitions about existence and uniqueness. At the heart of many multiverse theories lies the concept of mathematical infinity, not merely as an abstract mathematical notion, but as a concrete description of physical reality. In an infinite universe, or an infinite collection of universes, every possible arrangement of matter and energy must occur somewhere, repeated endlessly throughout the vast expanse of existence. Consider the implications of spatial infinity. If space extends infinitely in all directions and contains matter distributed with some average density, then every possible configuration of particles within any finite volume must be repeated infinitely, many times. This includes exact duplicates of our solar system, our planet, and even ourselves, living out identical lives in distant regions of an infinite cosmos. The mathematics of this replication follows from basic principles of combinatorics. Within any finite volume, there are only finitely many ways to arrange a finite number of particles. In an infinite space, these finite configurations must repeat, creating a hierarchy of identical regions at ever larger scales. At relatively small scales, we might find regions that differ from our local environment in only minor ways. Perhaps a world where you chose a different breakfast this morning, or where a particular cloud formed in a slightly different shape. As we consider larger regions, we encounter more dramatic variations, including worlds with different histories, different physical laws, or even entirely different forms of matter and energy. The mathematical structure known as the universal wave function provides another framework for understanding infinite realities. In the many worlds interpretation of quantum mechanics, this wave function describes not just our universe, but all possible universes simultaneously, encoding the amplitudes and phases associated with every possible configuration of matter and energy. This wave function evolves deterministically according to the Schrödinger equation, never losing information or probability. Every possible quantum event occurs somewhere within this vast mathematical structure, with the apparent randomness of individual measurements arising from our limited perspective as observers embedded within one branch of CAR, the universal evolution. The mathematical formalism reveals that the many worlds multiverse has the structure of an infinite dimensional Hilbert space, where each possible universe corresponds to a vector in this abstract mathematical B arena. The evolution of the multiverse corresponds to rotations in this space, preserving the total magnitude while redistributing probability amplitudes among the various branches. Set theory provides yet another mathematical framework for exploring infinite realities. The concept of cardinality reveals that there are different sizes of infinity, with some infinite sets being larger than others in a precise mathematical sense. The set of natural numbers is infinite, but the set of real numbers is uncountably infinite, representing a larger fall of infinity. These mathematical distinctions between different infinities might correspond to different levels of multiverse structure. The set of all possible quantum mechanical universes might be countably infinite, while the set of all possible mathematical structures might be uncountably infinite, suggesting hierarchies of reality that extend beyond anything describable by quantum mechanics alone. Max Tegmark's mathematical universe hypothesis takes this idea to its logical extreme, proposing that mathematical existence and physical existence are identical. In this view, every mathematically consistent structure exists as a physical reality, creating a multiverse that encompasses not only all possible solutions to the laws of physics, but all possible mathematical cabal structures whatsoever. This hypothesis suggests that our universe exists because it corresponds to a particular mathematical structure, not because it was created or selected by any external process. Other mathematical structures exist equally as other universes, creating a democracy of realities where no particular universe is more fundamental or real than any other. The implications of this mathematical multiverse are staggering. It would include universes governed by different mathematical logics, universes with different numbers of dimensions, universes where mathematical constants take different values, and universes where the very concept of space and time might be meaningless. Computational approaches to infinity provide another perspective on infinite realities. In computer science, the study of algorithmic information theory reveals deep connections between mathematical complexity and physical existence. This field suggests that simple mathematical structures are more likely to be instantiated as physical realities than complex ones. The principle of computational equivalence, explored in detail by Stephen Wolfram, suggests that simple computational rules can generate behaviors of unlimited complexity. This principle implies that even very simple mathematical structures might give rise to universes as rich and complex as our own. Cellular automata provide concrete examples of simple rules generating complex behavior. These mathematical systems consist of grids of cells that evolve according to local rules, yet they can exhibit phenomena as sophisticated as universal computation, self-reproduction, and emergent taffy complexity. If universes are mathematical structures that evolve according to computational rules, then the space of all possible universes might be equivalent to the space of all possible computations. This computational multiverse would include our universe as one particular program running on the vast computational substrate of mathematical reality. Recent developments in category theory and homotopy-type theory have provided new mathematical frameworks for understanding the structure of mathematical reality itself. These advanced mathematical theories suggest that the foundations of mathematics might be more flexible and varied than traditionally assumed. In these new foundations, mathematical truth is not absolute, but relative to the particular mathematical context or universe being considered. Different mathematical universes might have different logics, different notions of equality, and different ways of constructing mathematical objects. This perspective suggests that the mathematical universe hypothesis might need to be refined. Rather than encompassing all mathematical structures in some absolute sense, the physical multiverse might correspond to all possible mathematical foundations, each giving rise to its own collection of mathematical structures and corresponding physical realities. The study of formal systems and Gödel's incompleteness theorems adds another layer of complexity to these considerations. Gödel showed that any mathematical system complex enough to describe arithmetic contains statements that cannot be proved or disproved within the system itself. This incompleteness might reflect fundamental limitations in any mathematical description of reality. These limitations suggest that even an infinite multiverse of mathematical structures might not exhaust all possibilities. There might be aspects of reality that transcend any mathematical description, existing in a realm beyond the reach of formal systems and algorithmic computation. The landscape of string theory represents perhaps the most sophisticated mathematical framework for understanding parallel universes, revealing a vast terrain of possible realities that emerges naturally from the fundamental principles of the theory. This landscape encompasses not merely different arrangements of matter and energy, but different forms of physics itself, with varying numbers of dimensions, particle types, and fundamental forces. String theory's requirement for extra spatial dimensions creates an enormous space of possibilities through the process of compactification. The 6 or 7 extra dimensions must be curled up into complex geometric structures called Calabi-Yau manifolds, and the particular choice of manifold determines the physics observed in the resulting G-team. 4-dimensional world. Mathematicians have catalogued thousands of distinct Calabi-Yau manifolds, each corresponding to a different possible compactification of string theory. Some estimates suggest that the total number of topologically distinct compactifications could reach 10,500 or even higher, a number so vast that it exceeds the number of atoms in the observable Prash universe by an unimaginable margin. Each point in this landscape represents a different universe with its own set of physical laws. The masses of particles, the strengths of forces, the number of particle types, and even the number of observable spatial dimensions can vary from point to point in the landscape. Our universe corresponds to one particular point, characterized by the specific Calabi-Yau manifold that describes our local compactification. The topology of Calabi-Yau manifolds involves intricate mathematical structures with multiple holes, handles, and interconnected regions. These topological features trap strings in specific vibrational patterns, determining which particles exist and how they interact. A manifold with many small holes might produce a universe with numerous light particles, while a manifold with fewer, larger holes might yield fewer, heavier particles. Flux compactifications add another layer of complexity to the string landscape. These involve wrapping additional fields, called fluxes, around the various cycles and surfaces within the Calabi-Yau manifold. Different flux configurations can stabilize different geometric shapes and produce different particle physics. The number of possible flux compactifications grows exponentially with the complexity of the underlying Calabi-Yau manifold. For manifolds with many topological cycles, the number of distinct flux configurations can reach astronomical proportions, contributing to the vastness of the overall string landscape. Moduli stabilization represents one of the central challenges in string theory compactification. The geometric parameters that characterize a Calabi-Yau manifold, known as moduli, must be fixed at specific values to produce a stable universe with definite physical properties. Different stabilization mechanisms can select different points in the landscape, leading to different physics. The process of moduli stabilization often involves balancing competing effects from various sources of energy within the compactified space. Quantum corrections, flux energies, and brane tensions all contribute to determining the final shape and size of the extra dimensions. The delicate balance among these effects can produce multiple stable configurations, each corresponding to a different possible universe. Supersymmetry breaking adds yet another dimension to the string landscape. Supersymmetry, a mathematical symmetry that relates particles of different spins, must be broken in our universe to match observed particle physics. The mechanism and scale of supersymmetry breaking can vary across the landscape, producing universes with different particle spectra and force strengths. Different supersymmetry breaking scenarios can lead to dramatically different phenomenology. Some regions of the landscape might preserve supersymmetry at low energies, leading to universes with additional particle types and modified force relationships. Other regions might break supersymmetry completely, producing universes without any supersymmetric partners. The anthropic principle provides a potential filter for navigating the vast string landscape. While most points in the landscape might correspond to universes that are hostile to the formation of complex structures and life, only a tiny fraction might have the precise combination of properties needed for stars, planets, chemistry, and biology. This anthropic selection could explain why our universe appears to be fine-tuned for life. Rather than requiring a supernatural designer or an unlikely cosmic coincidence, the apparent fine-tuning might simply reflect the fact that we can only observe universes where our existence is possible. However, anthropic reasoning in the string landscape remains controversial. Critics argue that it abandons the goal of predicting unique values for physical constants, replacing testable science with untestable speculation about unobservable universes. Supporters counter that anthropic reasoning might be unavoidable if the landscape is genuinely vast and if eternal inflation populates all possible regions. The dynamics of landscape exploration involve processes that can move a universe from one point in the landscape to another. Tunneling events, driven by quantum fluctuations, can cause transitions between different compactifications, potentially changing the fundamental physics of a universe over cosmic time. These landscape transitions might occur through the nucleation of bubbles with different physics, similar to the bubble universes created by eternal inflation. A tunneling event could create a bubble where the extra dimensions are compactified differently, leading to different particle physics within the bubble. The rate of these transitions depends on the height of energy barriers between different regions of the landscape. Universes in deep valleys of the landscape potential are stable and long-lived, while universes on peaks or shallow plateaus might be unstable and prone to rapid transitions. Eternal inflation provides a mechanism for populating the string landscape, creating bubble universes that sample different regions of the vast space of possibilities. The combination of eternal inflation and the string landscape produces a multiverse of incredible richness, where every possible form of string physics is realized somewhere. This populated landscape offers a new perspective on the nature of physical law. Rather than being universal and immutable, the laws of physics might be local and contingent, determined by the particular region of the landscape where a universe happens to find itself. Recent developments in string theory have revealed additional structure within the landscape through the study of string dualities. These mathematical relationships show that apparently different points in the landscape can actually represent the same physics described from different perspectives. The web of dualities creates a complex network of connections throughout the landscape, suggesting that the space of distinct string theories might be smaller than the naive counting of Calabi-Yau manifolds would suggest. However, even accounting for these dualities, the landscape remains vast beyond comprehension. Machine learning and artificial intelligence are beginning to play important roles in exploring the string landscape. The complexity of Calabi-Yau geometry and flux compactification makes it impossible to study the entire landscape using traditional mathematical techniques. Advanced algorithms can help identify patterns and structures within the landscape that might be missed by human analysis. These computational approaches are revealing unexpected correlations and clusters within the landscape, suggesting that the space of string compactifications might have a richer structure than previously realized. Some regions of the landscape might be densely connected through dualities and transitions, while others might be relatively isolated. Cosmological constants and fine-tuning the apparent fine-tuning of physical constants represents one of the most puzzling and controversial aspects of modern cosmology, raising profound questions about the nature of physical law and the possibility of parallel universes with different fundamental parameters. The precision with which certain constants must be adjusted to permit the existence of stars, planets, chemistry, and life appears to exceed any reasonable expectation of cosmic coincidence. The cosmological constant problem exemplifies these fine-tuning puzzles in their most extreme form. This constant, which determines the energy density of empty space itself, affects the expansion rate of the universe and the formation of cosmic structure. Theoretical calculations suggest that quantum fluctuations should contribute an enormous positive value to this constant, roughly 10^120 times larger than the observed value. This discrepancy represents the worst theoretical prediction in the history of physics. If the cosmological constant had the theoretically expected value, the universe would expand so rapidly that matter could never clump together to form galaxies, stars, or planets. The observed value is not only much smaller than predicted, but actually positive and non-zero, causing the cosmic expansion to accelerate. The cosmological constant problem becomes even more perplexing when we consider the delicate balance required for cosmic structure formation. If the constant were significantly larger, the accelerated expansion would begin too early, preventing the formation of galaxies. If it was significantly smaller or negative, the universe might recollapse before stars could form and evolve. Other examples of apparent fine-tuning abound throughout physics. The strength of the strong nuclear force must be precisely adjusted to allow both the binding of protons and neutrons into nuclei and the stability of complex nuclei against decay. A small increase would cause all hydrogen to be converted to heavier elements during Big Bang nucleosynthesis, while a small decrease would prevent the formation of elements heavier than hydrogen. The electromagnetic force strength determines the stability of atoms and the efficiency of stellar fusion. Changes of more than a few percent would either prevent atoms from forming or cause stars to burn too quickly to support long-term planetary evolution. The delicate balance between electromagnetic and gravitational forces determines the size and lifetime of stars, with small changes leading to dramatically different stellar properties. The masses of fundamental particles also appear to be finely tuned. The electron mass determines the size of atoms and the binding energies of chemical bonds. The quark masses affect the stability of protons and neutrons, the efficiency of nuclear fusion, and the abundance of elements produced in stellar cores. Even more striking is the near equality of matter and antimatter densities in the early universe. These densities must have differed by less than 1 part in a billion to produce the observed matter abundance while avoiding complete annihilation. This tiny asymmetry, despite appearing highly improbable, was essential for the existence of any matter-based structures. The hierarchy problem in particle physics presents another form of fine-tuning. The Higgs boson mass, which determines the strength of the weak nuclear force and the masses of other particles, receives enormous quantum corrections that should drive it to much larger values. Keeping the Higgs mass at its observed value requires precise cancellations between different contributions, suggesting either fine-tuning or new physics beyond the standard model. These fine-tuning puzzles have inspired various responses from the physics community. Some researchers argue that future theoretical developments will reveal why the constants must have their observed values, eliminating the appearance of fine-tuning through deeper understanding of physical principles. Others propose that the constants are not actually fine-tuned but only appear so because of selection effects or observational biases. Perhaps there are ranges of parameter values that permit complex structures other than those we recognize as conducive to life, broadening the apparently narrow windows of viability. The multiverse hypothesis offers a radically different resolution to fine-tuning problems. If a vast number of universes exist with different values of physical constants, then some fraction will inevitably have parameters compatible with complex structure formation and biological evolution. We necessarily find ourselves in such a universe, not because it was specially designed, but because we could not exist elsewhere. This anthropic explanation transforms fine-tuning from a puzzle requiring special explanation into a natural consequence of observer selection in a diverse multiverse. The apparent improbability of our universe's parameters becomes no more surprising than finding ourselves on a habitable planet rather than in the vacuum of space. Eternal inflation provides a natural mechanism for generating the parameter diversity required for anthropic explanation. If inflation creates bubble universes with randomly varying constants, then the resulting multiverse will sample the full range of possible parameter values, including the rare combinations that permit protein, complexity, and life. String theory offers a more specific framework for parameter variation through its vast landscape of compactifications. Different regions of the string landscape correspond to different values of the effective four-dimensional constants, creating a multiverse where every possible combination of parameters is realized somewhere. The combination of eternal inflation and the string landscape produces what Leonard Susskind has called the anthropic landscape, a multiverse specifically structured to address fine-tuning problems through environmental selection. In this picture, our universe's apparent fine-tuning reflects the anthropic filtering of a much larger ensemble of possibilities. However, anthropic reasoning faces significant challenges and criticisms. The approach requires making probability distributions over different universes, but there is no agreed-upon method for defining such probabilities. Differing probability measures can lead to dramatically different anthropic predictions, undermining the explanatory power of the approach. The measure problem in cosmology addresses this fundamental ambiguity. In an eternally inflating multiverse, every possible event occurs infinitely many times, making it difficult to define meaningful probabilities for different outcomes. Various proposed measures lead to different conclusions about which types of universes should be most common. Critics also argue that anthropic reasoning abandons the traditional goal of science to predict unique values for physical constants. If any observed constant value can be explained anthropically by invoking appropriate multiverse diversity, then the approach becomes unfalsifiable and unscientific. Defenders of anthropic reasoning respond that the approach does make testable predictions in cases where anthropic constraints are not the dominant factor. For example, anthropic reasoning in the string landscape has led to specific predictions about the distribution of cosmological constant values, some of which can be tested observationally. Recent developments in theoretical physics have revealed new connections between fine-tuning and fundamental principles. Some proposed solutions to the hierarchy problem, such as supersymmetry and extra dimensions, naturally address multiple fine-tuning issues simultaneously, suggesting that deeper physical principles might underlie the apparent coincidences. The swampland program in string theory has identified constraints that any consistent quantum theory of gravity must satisfy. These swampland criteria might restrict the possible values of physical constants, potentially reducing the fine-tuning required for viable universes. Environmental selection provides another mechanism that might reduce apparent fine-tuning without invoking parallel universes. If physical constants can vary over cosmic time or space within a single universe, then regions with different parameter values might coexist, with complex structures forming preferentially in regions with Canonical suitable conditions. The continuing study of fine-tuning problems remains an active area of research, driving advances in theoretical physics, cosmology, and philosophy of science. Whether these puzzles point toward multiverse explanations, deeper physical principles, or entirely new frameworks for understanding reality remains an open question that will likely shape the future development of fundamental physics. Observable consequences and tests the question of whether parallel universes are merely mathematical speculation or genuine physical reality hinges crucially on whether these theories make testable predictions that can be verified through observation and experiment. While parallel universes may seem inherently unobservable, several proposed mechanisms could leave detectable signatures in our universe, opening windows into the broader multiverse structure. The cosmic microwave background radiation provides the most promising laboratory for detecting multiverse signatures. This ancient light, released when the universe became transparent about 380,000 years after the Big Bang, carries detailed information about the conditions in the early universe, including potential evidence of interactions with other universes. Bubble collisions in eternal inflation could leave distinctive imprints on the cosmic microwave background. If our universe collided with another bubble universe during its early evolution, the collision would create patterns of temperature fluctuations that differ from those produced by ordinary inflation. These collision signatures would appear as specific geometric patterns, such as rings or disk-like features, superimposed on the usual random fluctuations. Several research groups have searched for such collision signatures in cosmic microwave background data from satellites like WMAP and Planck. While no definitive detections have been claimed, these searches have placed constraints on the frequency and strength of possible bubble collisions, providing the first observational limits on certain multiverse models. The detailed statistical properties of cosmic microwave background fluctuations also carry information about the underlying inflationary process and its potential multiverse implications. Eternal inflation models make specific predictions about the distribution of fluctuation amplitudes and the correlations between fluctuations at different scales. Non-Gaussianity in the cosmic microwave background represents another potential multiverse signature. Most simple inflation models predict that temperature fluctuations should follow a Gaussian distribution, but interactions between our universe and other regions of the multiverse could introduce deviations from this prediction. Gravitational wave observations open another observational window into the early universe and potential multiverse phenomena. Cosmic inflation is predicted to produce gravitational waves that would leave distinctive polarization patterns in the cosmic microwave background radiation. The detection of these primordial gravitational waves would provide strong evidence for inflation and potentially reveal information about the multiverse structure. Advanced gravitational wave detectors like LIGO, Virgo, and future space-based instruments might also detect gravitational waves from exotic sources related to multiverse physics. Phase transitions between different regions of the string landscape, brane collisions in extra dimensions, or the formation of cosmic strings could all produce gravitational wave signals with characteristic signatures. Dark matter and dark energy provide additional probes of multiverse physics. If our universe's dark matter arises from particles that can interact with parallel universes through extra dimensions, these interactions might leave observable signatures in dark matter distributions, collision experiments. The mysterious dark energy that drives cosmic acceleration could itself be a multiverse phenomenon. Some models propose that dark energy arises from interactions between our universe and other branes in higher dimensional space, leading to specific predictions about how dark energy density changes over cosmic time. Particle physics experiments at high-energy accelerators like the Large Hadron Collider could reveal evidence for extra dimensions and parallel universes through several mechanisms. Missing energy signatures could indicate particles escaping into extra dimensions, while the production of microscopic black holes or other exotic objects could reveal the presence of hidden spatial dimensions. Supersymmetry searches at collider experiments connect to multiverse physics through the string landscape. The discovery of supersymmetric particles would support string theory and its multiverse implications, while their continued absence places constraints on which regions of the string landscape might be realized in nature. Precision measurements of physical constants over cosmic time could reveal evidence for multiverse structure. If our universe is gradually transitioning from one region of the string landscape to another, the fundamental constants might slowly drift over billions of years. Astronomical observations of distant galaxies and quasars can search for such temporal variations. Spatial variations in physical constants could also provide multiverse signatures. If our observable universe spans regions with slightly different parameter values, we might detect gradual changes in constant values across the sky. Such variations would violate the cosmological principle that could arise naturally in certain multiverse scenarios. Quantum mechanics experiments continue to test the foundations of the many worlds interpretation through increasingly sophisticated demonstrations of quantum superposition and entanglement. While these experiments cannot directly detect parallel worlds, they can test the consistency of many worlds predictions and explore the boundaries between quantum and classical behavior. Bell test experiments with ever greater precision and sophistication continue to verify the non-local correlations predicted by quantum mechanics, ruling out classical alternatives and supporting interpretations that invoke parallel realities or fundamental non-locality. Quantum computing and quantum information experiments probe the computational resources available in quantum systems, potentially revealing evidence for the vast Hilbert space structure predicted by many worlds theories. The exponential speedup demonstrated by quantum computers is consistent with the idea that quantum systems can access computational resources from parallel branches of reality. The development of quantum error correction and fault-tolerant quantum computation provides new tools for maintaining quantum coherence over extended periods, potentially allowing more sophisticated tests of quantum foundations and multiverse theories. Astronomical searches for signatures of different physics in distant regions of our universe could reveal evidence for spatial variations in fundamental laws. If different regions of space have slightly different compactifications or parameter values, these variations might be detectable through careful analysis of stellar spectra, galaxy formation patterns, or large QE. Scale structure. The study of cosmic voids, the largest empty regions in the universe, might reveal evidence for multiverse structure. Some models predict that these voids could be remnants of interactions with other universes or regions where different physics applies. Future astronomical surveys with unprecedented precision and scope will provide new opportunities to search for multiverse signatures. Projects like the James Webb Space Telescope, the Extremely Large Telescope, and the Square Kilometre Array will observe the universe with sensitivity levels that could reveal subtle effects of parallel Besserian universe interactions. The interpretation of null results in multiverse searches presents significant challenges. The absence of detected signatures could indicate that multiverse effects are too small to observe, that they occur in ways we haven't anticipated, or that multiverse theories are simply incorrect. Distinguishing between these possibilities requires careful theoretical work and increasingly sensitive experimental techniques. Statistical analysis of multiverse searches must account for the look elsewhere effect, where the probability of finding apparent signals increases when searching for many different types of signatures. Rigorous statistical methods are needed to assess the significance of potential multiverse detections. The philosophy of multiple realities, the concept of parallel universes, extends far beyond the realm of physics, touching on fundamental questions in philosophy that have preoccupied human thought for millennia. These questions involve the nature of existence, the meaning of identity, the relationship between possibility and actuality, and the very foundations of knowledge and reality. The ontological status of parallel universes represents perhaps the most basic philosophical challenge. If infinite universes exist beyond our ability to observe or interact with them, in what sense can we say they are real? Traditional scientific methodology relies on empirical verification through observation and experiment, yet parallel universes seem to exist permanently beyond the reach of direct observation. This challenge echoes ancient philosophical debates about the nature of existence itself. Plato's theory of forms proposed that perfect mathematical objects exist in a realm beyond physical reality, accessible only through pure thought. Similarly, parallel universes might exist in a realm that is physically real but observationally inaccessible, challenging our concepts of what constitutes genuine existence. The relationship between mathematical existence and physical reality becomes particularly acute in discussions of parallel universes. Max Tegmark's mathematical universe hypothesis suggests that mathematical existence is sufficient for physical existence, meaning that every mathematically consistent structure exists as a physical reality somewhere in the vast landscape of possible worlds. This proposal raises profound questions about the nature of mathematical objects. Are numbers, geometric shapes, and abstract structures discovered or invented by human minds? If mathematical objects exist independently of human thought, might they serve as the foundation for multiple physical realities, each corresponding to a different mathematical structure? The problem of personal identity takes on new dimensions in a multiverse context. If infinite copies of yourself exist across parallel universes, which one is the real you? Philosophy has long grappled with questions about personal identity over time. What makes you the same person you were 10 years ago, despite the complete replacement of every atom in your body? Parallel universe scenarios add spatial and modal dimensions to these temporal puzzles. If another version of you exists in a distant region of space or in a parallel quantum branch, that version shares your history up to some point but then diverges. The relationship between you and your parallel selves raises questions about the nature of consciousness, memory, and personal continuity. The branching structure of the many worlds interpretation creates particularly intricate identity puzzles. If quantum measurements constantly split you into multiple copies, each experiencing different outcomes, which branch contains the real continuation of your consciousness? The many worlds interpretation suggests that this question is meaningless. Each branch contains an equally valid version of you with equal claim to being your genuine continuation. These considerations extend to moral and ethical questions about responsibility and action. If every possible choice you might make is actually made by some version of you in the multiverse, what is the significance of moral decision-making? Does it matter which choice you make if all alternatives are realized somewhere else? Some philosophers argue that multiverse contexts actually increase rather than diminish moral responsibility. Even if other versions of you make different choices, the particular version that is, you must still choose wisely within its own branch of reality. The existence of parallel selves does not absolve you of responsibility for your own actions. The principle of indifference raises additional challenges for multiverse ethics. If all possible outcomes occur somewhere in the multiverse, how should we assign value to different possibilities? Traditional utilitarian ethics might suggest that we should try to maximize the overall happiness across all branches, but this leads to paradoxes when infinite branches are involved. Modal realism, the philosophical doctrine that possible worlds are as real as the actual world, provides a framework for thinking about parallel universes that predates modern physics. David Lewis argued that possible worlds exist as concrete physical realities, differing from our world not in their degree of existence, but only in their causal isolation from us. This philosophical position aligns remarkably well with certain interpretations of parallel universe theories in physics. The many worlds interpretation of quantum mechanics and the eternal inflation multiverse both propose that alternative realities exist as concrete physical systems, separated from us by quantum branching or cosmological distance rather than mere logical possibility. The verification principle in philosophy of science poses significant challenges for multiverse theories. This principle, associated with logical positivism, suggests that scientific statements are meaningful only if they can be verified through observation or logical analysis. Since parallel universes appear to be permanently unobservable, the verification principle would classify multiverse theories as meaningless metaphysical speculation. However, many philosophers of science have moved beyond strict verificationism, recognizing that scientific theories often refer to unobservable entities and processes. Electrons, quarks, and quantum fields are not directly observable, yet they play essential roles in our best scientific theories. The question becomes whether parallel universes are similar to these accepted unobservables or represent a qualitatively different category of theoretical entity. The underdetermination of scientific theories by empirical evidence provides another philosophical perspective on multiverse questions. Multiple theories can often account for the same observational data, making it difficult to determine which theory is correct based on evidence alone. Parallel universe theories represent an extreme case of underdetermination, where the existence of vast unobservable realities depends on theoretical considerations rather than direct empirical support. Philosophical naturalism, the view that scientific methods provide the best route to understanding reality, offers support for taking multiverse theories seriously. If our best scientific theories naturally lead to multiverse conclusions, naturalistic philosophers argue that we should accept these implications even if they conflict with common sense or traditional Baal. Philosophical assumptions. The anthropic principle connects parallel universe theories to broader questions about explanation and scientific methodology. Some philosophers argue that anthropic reasoning represents a legitimate form of scientific explanation, while others contend that it abandons the goal of finding law-like regularities in favor of selection, effects, and probabilistic arguments. The fine-tuning of physical constants raises questions about the nature of scientific explanation itself. Traditional reductionist approaches seek to explain complex phenomena in terms of simpler underlying principles. Multiverse explanations of fine-tuning work differently, explaining apparent design through selection from a vast ensemble of possibilities rather than through fundamental necessity. Consciousness presents perhaps the deepest philosophical challenge in multiverse contexts. If multiple copies of your brain exist across parallel universes, each processing information and generating experiences, what determines which conscious experience you actually have? The binding problem in consciousness research asks how unified conscious experience emerges from distributed neural processing, and multiverse theories add new dimensions to this puzzle. Some interpretations of quantum mechanics propose that consciousness plays a fundamental role in determining physical reality through the process of observation and measurement. If consciousness can influence which branch of the quantum multiverse becomes actualized, then the relationship between mind and physical reality becomes deeply interconnected. The problem of other minds, how we can know that other people have conscious experiences similar to our own, becomes even more complex in multiverse settings. If infinite versions of other people exist across parallel realities, what is the relationship between their various conscious experiences and the particular instances we encounter in our branch of reality? Philosophical skepticism finds new forms of expression in multiverse contexts. If we are just one of infinitely many conscious observers distributed across a vast multiverse, how can we be confident that our observations and reasoning provide reliable information about reality? The possibility that we exist in an atypical or deceptive region of the multiverse creates new versions of classical skeptical scenarios. The simulation hypothesis represents a modern version of these skeptical challenges. If advanced civilizations can create realistic simulations of conscious beings, and if such simulations become common, then most conscious observers might exist within simulations rather than in fundamental reality. Multiverse theories could increase the probability of living in a simulation by providing more opportunities for advanced civilizations to emerge. Free will and determinism take on new meanings in multiverse contexts. If all possible choices are made by different versions of yourself across parallel branches, is free will merely an illusion arising from your limited perspective on the vast tree of possibilities? Alternatively, the many worlds interpretation might preserve free will by ensuring that every possible choice is genuinely made somewhere in the multiverse. The relationship between physics and philosophy becomes particularly intimate in multiverse discussions. Traditional boundaries between empirical science and conceptual analysis become blurred when theories make claims about vast, unobservable realities that challenge fundamental assumptions about existence, identity, and knowledge. Cultural impact and science fiction, the concept of parallel universes, has captured the human imagination far beyond the confines of academic physics and philosophy, inspiring countless works of literature, film, television, and other forms of cultural expression. These creative explorations have not only entertained audiences, but also helped shape public understanding of multiverse concepts and influence the questions that scientists and philosophers ask about the nature of reality. Science fiction literature was among the first cultural domains to explore parallel universe themes systematically. Early works like Edwin Abbott's Flatland introduced readers to the possibility of higher dimensional spaces, while authors like H.G. Wells explored time travel scenarios that implicitly involved alternative timelines and parallel histories. The golden age of science fiction in the mid-20th century saw an explosion of parallel universe stories. Writers like Isaac Asimov, Philip K. Dick, and Robert Heinlein created narratives that explored the implications of multiple realities for personal identity, free will, and the nature of existence itself. These stories often anticipated concepts that would later emerge in serious scientific discussions. Philip K. Dick's works proved particularly prescient in their exploration of reality and consciousness in multiverse settings. His novel, The Man in the High Castle, depicted an alternative history where the Axis powers won World War II, while Ubik explored questions about the nature of reality and the persistence of consciousness after death. Dick's paranoid and reality-questioning narratives anticipated many of the philosophical puzzles that arise in modern multiverse theories. The concept of alternative histories became a major subgenre of science fiction, with authors exploring how different choices and events might have led to dramatically different worlds. These counterfactual narratives serve as thought experiments about causation, contingency, and the role of individual agency in shaping historical outcomes. Comic book universes provided another fertile ground for parallel universe storytelling. The DC Comics multiverse, introduced in the 1960s, featured multiple versions of familiar superheroes existing on parallel Earths with different histories and characteristics. Marvel Comics developed similar concepts, creating vast interconnected networks of alternative realities that could interact through cosmic events and dimensional travel. These comic book multiverses served important narrative functions, allowing writers to explore different versions of beloved characters and to reset continuity when storylines became too complex or contradictory. The concept of crisis events that merged or destroyed multiple universes provided dramatic storytelling opportunities while addressing practical publishing concerns. Television series embraced parallel universe concepts with increasing sophistication over the decades. Shows like The Twilight Zone and Star Trek featured episodes exploring alternative realities and moral thought experiments. Later series like Sliders, Fringe, and Rick and Morty made parallel universes central to their ongoing narratives. Rick and Morty deserves particular mention for its scientifically informed exploration of multiverse concepts. The show incorporates ideas from quantum mechanics, eternal inflation, and modal realism while using them to explore themes of nihilism, meaning, and personal responsibility in a context where infinite trash alternatives exist. Film adaptations of parallel universe concepts have ranged from philosophical art films to blockbuster entertainment. Movies like Sliding Doors, The Matrix, and Everything Everywhere All at Once have brought multiverse ideas to mainstream audiences, each offering different perspectives on the implications of multiple realities. Everything Everywhere All at Once represents a particularly sophisticated engagement with multiverse themes, incorporating elements from both scientific theories and philosophical traditions. The film explores how the existence of infinite alternatives might initially seem overwhelming and meaningless, but ultimately emphasizes the importance of choosing to focus on the particular reality we inhabit. The influence has flowed in both directions, with science fiction concepts influencing scientific thinking as well as being influenced by it. Scientists like Max Tegmark and Brian Greene have acknowledged that science fiction narratives help them think about the implications of their theories and communicate complex ideas to broader audiences. Virtual reality and video game technologies have created new possibilities for experiencing parallel universe narratives interactively. Games like BioShock Infinite and Life is Strange allow players to make choices that lead to different outcomes, creating branching narratives that mirror the structure of quantum mechanical many worlds theories. The concept of alternate reality games, ARG, creates immersive experiences that blur the boundaries between fiction and reality. These games use multiple media platforms and real-world elements to create the illusion that players are uncovering hidden truths about parallel realities or secret histories. Multimedia franchises have embraced multiverse concepts as ways to expand their storytelling possibilities while maintaining continuity across different media. The Marvel Cinematic Universe has increasingly incorporated multiverse elements, allowing for the inclusion of different versions of characters from various film series and comic book timelines. The cultural impact of parallel universe concepts extends beyond entertainment into broader social and political discussions. The idea that alternative histories might have led to different present realities influences how people think about counterfactual scenarios and the contingency of current social arrangements. Educational initiatives have used parallel universe concepts to engage students with physics and philosophy topics that might otherwise seem abstract or irrelevant. The dramatic and imaginative aspects of multiverse theories help capture student interest while introducing fundamental concepts about the nature of space, time, matter, and consciousness. Popular science communication has been transformed by the availability of parallel universe metaphors and narratives. Scientists writing for general audiences can draw on familiar science fiction tropes to explain complex theoretical concepts, making advanced physics more accessible to non-specialists. The cultural fascination with parallel universes reflects deeper human concerns about choice, identity, and meaning. In an increasingly complex and interconnected world, the idea that alternative possibilities exist somewhere else provides both comfort and anxiety. The notion that every choice creates branching realities suggests that all possibilities are preserved, even as it raises questions about the significance of any particular choice. Religious and spiritual communities have engaged with parallel universe concepts in various ways, sometimes seeing them as supporting ideas about multiple planes of existence or infinite divine creativity. Other religious thinkers have criticized multiverse theories as undermining the specialness of creation or the importance of moral choice. The democratization of information through the internet has allowed multiverse concepts to spread rapidly through popular culture, sometimes in simplified or distorted forms. Social media platforms enable the rapid sharing of multiverse-related content, from serious scientific discussions to humorous memes that play with the implications of infinite alternative realities. The psychological appeal of parallel universe concepts seems to stem from their ability to address fundamental human anxieties about choice, regret, and limitation. The idea that other versions of ourselves exist who made different choices provides a kind of cosmic consolation for the paths not taken in our own lives. This psychological dimension helps explain why parallel universe narratives continue to resonate with audiences across different cultural contexts and time periods. The themes they explore, identity, choice, reality, meaning, are universal human concerns that find new expression through the lens of modern physics and cosmology. Mythology and ancient concepts long before modern physics began to seriously consider the possibility of parallel universes, human cultures across the globe developed rich mythological and religious prasin, traditions that explored remarkably similar themes. These ancient narratives often featured multiple worlds, alternative realities, and cosmic structures that bear striking resemblances to concepts emerging from contemporary theoretical physics. The Norse cosmology presents one of the most elaborate ancient multiverse scenarios. The world tree, Yggdrasil, supported 9 distinct realms, each with its own inhabitants, laws, and characteristics. Asgard housed the gods, Midgard contained humans, and 7 other realms provided homes for various beings including giants, elves, and the dead. These worlds were connected through the branches and roots of the cosmic tree, allowing for travel and interaction between different levels of reality. This Norse multiverse was not merely a collection of separate spaces, but a dynamic system where events in one realm could influence conditions in others. The prophesied Ragnarök would bring about the destruction and renewal of the entire cosmic structure, suggesting cyclical time and regenerative processes that echo modern cosmological theories about cosmic cycles and universe formation. Hindu cosmology developed equally sophisticated concepts of multiple realities and cosmic cycles. The tradition describes countless universes existing simultaneously, each governed by its own cosmic cycles of creation, preservation, and destruction. These universes emerge from the breath of Brahma and exist for vast periods of time before dissolving back into the primordial source. The Hindu concept of kalpas, cosmic days lasting billions of years, parallels modern ideas about cosmic inflation and eternal universe creation. Each kalpa contains multiple cycles of creation and destruction, suggesting an infinite regress of cosmic time that resonates with eternal inflation scenarios where bubble universes continuously form in and ra. Ever-expanding space-time. Buddhist cosmology presents a 3-dimensional multiverse structure with multiple levels of existence arranged vertically according to the consciousness and karma of their inhabitants. This cosmic hierarchy includes numerous heaven realms, earth realms, and hell realms, each providing different conditions for the evolution of consciousness. The Buddhist concept of interdependence suggests that all these realms are intimately connected through networks of causation that transcend individual worlds. Actions in one realm influence conditions in others through complex karmic relationships, creating a kind of cosmic entanglement that mirrors the non-local correlations discovered in quantum mechanics. Chinese mythology and philosophy contributed concepts of parallel dimensions through Taoist ideas about hidden realms and alternative realities. The tradition speaks of immortal beings who exist in dimensions parallel to ordinary reality, accessible through specific practices or locations where the boundaries between worlds become permeable. The I Ching, or Book of Changes, presents a sophisticated system for understanding how different possible futures might unfold from present conditions. Its hexagram system maps out a landscape of possible situations and transformations, suggesting that multiple potential realities coexist and can be accessed through divination and wisdom. Ancient Egyptian mythology included elaborate descriptions of multiple afterlife realms, each with distinct characteristics and requirements for access. The journey through the underworld involved navigating a complex geography of alternative realities, each testing different aspects of the soul's development and understanding. The Egyptian concept of the Duat, or underworld, functioned as a parallel dimension existing alongside the physical world, but governed by different laws and populated by different beings. This parallel realm was not merely a destination after death, but an active dimension that influenced events in the physical world through the actions of gods and spirits. Greek mythology contributed the idea of alternate fates and parallel destinies through the concept of the fates, who weave the threads of individual lives and cosmic destiny. The tradition also includes numerous stories of heroes traveling to underworlds, alternate dimensions, and enchanted realms that exist alongside ordinary reality. Plato's allegory of the cave presents perhaps the most philosophically sophisticated ancient exploration of alternative realities. The prisoners chained in the cave mistake shadows on the wall for reality itself, unaware of the fuller world of forms that exists beyond their limited perception. This metaphor suggests that our ordinary experience might be merely a shadow of deeper realities existing in parallel dimensions of truth and being. Celtic mythology developed rich traditions around the otherworld, a parallel reality that coexists with the ordinary world but remains normally hidden from human perception. This otherworld could be accessed through specific portals during certain times or by individuals with special knowledge or abilities. The Celtic otherworld was not a distant realm, but an alternative layer of reality occupying the same space as the physical world. Hills, lakes, and forests might serve as doorways between dimensions, allowing interaction between the ordinary world and its magical parallel. This interpenetration of realities resembles modern ideas about extra dimensions that exist alongside our familiar three-dimensional space. Aboriginal Australian cosmology presents the concept of the dream time, an eternal parallel reality where the ancestral spirits created the landscape and established the laws governing both physical, spiritual existence. The dream time exists simultaneously with ordinary time, accessible through ritual, dream, and sacred sites. This Aboriginal worldview suggests that multiple temporal dimensions coexist, with mythic time running parallel to historical time and providing the foundational structure for all existence. The concept anticipates modern ideas about the block universe in relativity theory, where all moments in time exist simultaneously in a higher dimensional structure. Native American traditions across numerous tribes developed concepts of multiple worlds layered above and below the ordinary reality. These worlds often corresponded to different levels of spiritual development and were connected through sacred locations, vision quests, and shamanic journeys. The Hopi tradition describes multiple previous worlds that were destroyed when they became corrupted, with survivors moving to new worlds that represented fresh starts for human civilization. This cyclical cosmology suggests that parallel realities might exist sequentially rather than simultaneously, with each world representing a different phase in cosmic evolution. Shamanic traditions worldwide developed sophisticated practices for navigating alternative realities and parallel dimensions. Shamans in cultures from Siberia to South America describe journeys to upper and lower worlds populated by spirits, ancestors, and archetypal beings who influence events in ordinary reality. These shamanic cosmologies present multiverse structures where different levels of reality serve different functions in the overall cosmic order. The shamanic role involves mediating between these dimensions, bringing information and healing power from parallel realms into ordinary reality. The Kabbalistic tradition in Jewish mysticism developed detailed maps of multiple worlds and dimensions through the concept of the Sephirot and the Tree of Life. This system describes 10 interconnected spheres of existence, each with its own characteristics and corresponding to different aspects of divine emanation. The Kabbalistic multiverse presents a hierarchy of realities emanating from a source that transcends all dimensional limitations. Each level of reality reflects the others while maintaining its own unique properties, creating a cosmic structure that resembles modern ideas about holographic principles and dimensional reduction. Islamic cosmology includes concepts of multiple heavens and unseen worlds that coexist with physical reality. The tradition describes 7 heavens arranged in layers, each more refined and spiritual than the one below, suggesting a multiverse structure organized according to principles of consciousness and divine proximity. The concept of the barzakh, or intermediate realm between physical life and the afterlife, presents another parallel dimension that exists alongside ordinary reality but follows different temporal and spatial laws. This intermediate realm serves as a bridge between different levels of existence, facilitating communication and influence across dimensional boundaries. These ancient multiverse concepts demonstrate that the human imagination has long been drawn to ideas about multiple realities and parallel dimensions. While these mythological systems differ from modern scientific theories in their specific details and explanatory frameworks, they share common themes about the vastness of existence, the possibility of alternative realities, and the interconnectedness of different levels of being. The persistence of these themes across cultures and centuries suggests that multiverse concepts address fundamental aspects of human experience and consciousness. The sense that reality might be larger and stranger than immediate perception suggests has motivated both ancient mythological speculation and modern scientific investigation. The relationship between these mythological traditions and contemporary physics raises interesting questions about the sources of human insight into the nature of reality. While ancient cultures lacked the mathematical tools and experimental methods of modern science, their intuitive explorations of cosmic structure often anticipated ideas that have emerged from rigorous tasks, theoretical investigation. Whether these parallels represent genuine insights into the structure of reality, universal patterns in human consciousness, or mere coincidence remains an open question. However, the convergence of ancient wisdom and modern science in contemplating multiple realities suggests that multiverse concepts touch on something fundamental about the nature of existence itself. Modern physics and experimental evidence, the journey from philosophical speculation to scientific theory, requires the development of mathematical frameworks, theoretical predictions, and experimental tests that can distinguish between different possibilities. Modern physics has made remarkable progress in transforming parallel universe concepts from pure speculation into serious scientific hypotheses that make testable predictions about observable phenomena. Quantum mechanics provides the most direct experimental evidence for phenomena that point toward parallel universe interpretations. The double-slit experiment, first performed with light and later with electrons, atoms, and even large molecules, demonstrates that individual particles can apparently travel through multiple paths simultaneously, creating interference patterns that are impossible to explain without some form of superposition. When detectors are placed at the slits to determine which path each particle takes, the interference pattern disappears, and the particles behave like classical projectiles. This dramatic change in behavior, triggered solely by the act of measurement, suggests that the act of observation fundamentally alters the nature of physical reality. The many-worlds interpretation provides an elegant explanation for these observations without invoking mysterious wave function collapse. In this view, the particle actually does travel through both slits, but in different branches of reality. The measurement process causes the observer to become entangled with the particle, splitting into multiple versions that each observe a different outcome. More recent experiments have pushed the boundaries of quantum superposition to larger and more complex systems. Researchers have demonstrated quantum interference effects with molecules containing hundreds of atoms, showing that the quantum world is not limited to microscopic scales, but extends to objects that bridge the gap between quantum and classical physics. The observation of quantum superposition in macroscopic systems provides increasingly direct evidence for the universal applicability of quantum mechanics. Superconducting circuits have been placed in superposition states where electrical currents flow in opposite directions simultaneously, creating laboratory demonstrations of Schrödinger's cat-like scenarios. Quantum entanglement experiments have repeatedly confirmed the non-local correlations predicted by quantum mechanics, ruling out classical explanations based on local hidden variables. These experiments demonstrate that quantum systems can be correlated in ways that transcend the classical boundaries of space and time. Bell test experiments have become increasingly sophisticated, closing various loopholes that might allow classical explanations for quantum correlations. The most advanced experiments use space-based satellites to create entangled photon pairs separated by thousands of kilometers, demonstrating that quantum non-locality operates across astronomical distances. The development of quantum technologies has provided new tools for exploring the foundations of quantum mechanics and their implications for parallel universe theories. Quantum computers rely on maintaining superposition states long enough to perform useful calculations, requiring unprecedented control over quantum decoherence processes. The operation of quantum computers provides indirect evidence for the vast computational resources that become available when quantum superposition is preserved. The exponential speedup demonstrated by quantum algorithms like Shor's factoring algorithm suggests that quantum systems can access computational resources that grow exponentially with the number of particles involved. This exponential scaling of quantum resources aligns with the many worlds interpretations claim that quantum computers derive their power from performing computations across multiple parallel branches of reality. While this interpretation remains controversial, the practical success of quantum computing lends credence to theories that invoke vast hidden realities. Cosmological observations provide another source of evidence relevant to parallel universe theories. The cosmic microwave background radiation carries detailed information about the conditions in the early universe, including potential signatures of processes that might generate multiple universes. Measurements of cosmic microwave background fluctuations have confirmed many predictions of inflation theory, including the nearly stale invariant spectrum of density fluctuations and the statistical properties of temperature variations across the sky. These confirmations lend support to inflation theory and its potential multiverse implications. Searches for non-Gaussianity in cosmic microwave background data could reveal signatures of interactions between our universe and other regions of a larger multiverse. While no definitive non-Gaussian signals have been detected, these searches have placed constraints on certain classes of multiverse models. The discovery of dark energy and the acceleration of cosmic expansion has opened new avenues for testing multiverse theories. The observed value of the cosmological constant falls within the narrow range required for structure formation, but theoretical calculations suggest that most regions of a multiverse would have vastly different values. This apparent fine-tuning of the cosmological constant can be explained anthropically if our universe is part of a larger multiverse where different regions have different vacuum energy densities. The anthropic explanation predicts that the observed cosmological constant should be near the upper limit compatible with galaxy formation, which appears to match observations. Precision measurements of other physical constants have searched for evidence of spatial or temporal variations that might indicate multiverse structure. While no significant variations have been detected, these null results place constraints on models where physical constants can vary across cosmic space or time. Particle physics experiments at high-energy colliders provide tests of theories that naturally lead to multiverse scenarios. The discovery of the Higgs boson confirmed the existence of the scalar field that gives mass to other particles, but the measured Higgs mass creates puzzles that might require multiverse explanations. The hierarchy problem arises because quantum corrections should drive the Higgs mass to much larger values than observed. Solutions to this problem often invoke supersymmetry, extra dimensions, or other physics beyond the standard model that naturally lead to multiverse scenarios. Searches for supersymmetric particles, extra dimensions, and other exotic phenomena continue at experiments like the Large Hadron Collider. While no definitive discoveries have been made, these searches place increasingly stringent constraints on the parameter space of theories that predict multiverse structure. The development of gravitational wave astronomy has opened an entirely new window for observing the universe and potentially detecting signatures of multiverse physics. Gravitational waves from the early universe could carry information about inflation, phase transitions, and other processes that might generate parallel universes. Future gravitational wave detectors with increased sensitivity might be able to observe primordial gravitational waves from cosmic inflation, providing direct evidence for the process that could generate, quote, eternal inflation and bubble universes. These observations would represent a major step toward testing multiverse theories. The study of black hole physics has revealed deep connections between gravity, quantum mechanics, and information theory that have implications for multiverse scenarios. The black hole information paradox suggests that information falling into black holes is not destroyed but preserved in ways that might involve parallel realities or hidden dimensions. Recent theoretical developments suggest that black holes might be connected to other regions of spacetime through quantum entanglement, creating networks of correlation that transcend classical spacetime boundaries. These ideas connect black hole physics to holographic principles and multiverse theories. The ongoing search for quantum gravity theories continues to reveal new perspectives on the nature of spacetime and its possible multiverse structure. String theory, loop quantum gravity, and other approaches to quantum gravity naturally incorporate ideas about extra dimensions, multiple universes, and the emergence of spacetime from more fundamental prey, quantum processes. Experimental tests of quantum gravity remain challenging due to the enormous energy scales involved, but increasingly sensitive experiments are probing the boundaries between quantum mechanics and general relativity. These experiments might eventually reveal signatures of extra dimensions, discrete spacetime structure, or other features that point toward multiverse scenarios. The accumulation of experimental evidence supporting quantum mechanics, confirming inflation theory, and revealing the strange properties of dark energy creates an increasingly compelling case for taking multiverse theories seriously. While direct observation of parallel universes remains impossible, the indirect evidence continues to mount. The development of new experimental techniques and more sensitive instruments promises to provide additional tests of multiverse theories in the coming decades. Whether these tests will confirm, refute, or refine our understanding of parallel universes remains to be seen, but the scientific method continues to provide tools for exploring even the most exotic possibilities. The future of multiverse research, the study of parallel universes, stands at the threshold of a new era, driven by rapid advances in theoretical physics, observational cosmology, and quantum technology. The coming decades promise to bring unprecedented opportunities for testing multiverse theories and exploring the deepest questions about the nature of reality itself. Quantum computing represents one of the most promising frontiers for exploring multiverse implications. As quantum computers become more powerful and sophisticated, they will provide increasingly direct probes of the quantum mechanical foundations that underlie many worlds' theories. The exponential scaling of quantum computational resources offers a potential window into the vast hidden realities that parallel universe theories propose. Near-term quantum computers with hundreds or thousands of qubits will enable simulations of quantum systems too complex for classical computers to handle. These simulations will provide new insights into quantum decoherence, entanglement dynamics, and the emergence of classical behavior from quantum foundations. The development of fault-tolerant quantum computers will allow for unprecedented tests of quantum mechanics over extended time periods. These experiments might reveal subtle deviations from standard quantum predictions that could point towards specific interpretations of quantum mechanics or new physics beyond current theories. Quantum error correction protocols are themselves providing new insights into the relationship between information, space, and time. The discovery that spacetime geometry might emerge from quantum error correction processes suggests deep connections between multiverse theories and the fundamental structure of reality. Advanced gravitational wave detectors promise to open new observational windows into the early universe and potential multiverse phenomena. Third-generation ground-based detectors like the Einstein telescope and Cosmic Explorer will have sensitivities orders of magnitude greater than current instruments. Space-based gravitational wave observatories like the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from sources inaccessible to ground-based detectors. These instruments might observe primordial gravitational waves from cosmic inflation, providing direct evidence for the process that could generate eternal inflation and bubble universes. The combination of multiple gravitational wave detectors across the globe will enable precise triangulation of gravitational wave sources and detailed studies of their properties. These networks might detect exotic sources related to extra dimensions, phase transitions between different vacuum states, or other multiverse phenomena. Next-generation cosmological surveys will map the large-scale structure of the universe with unprecedented precision, searching for subtle signatures of multiverse interactions. Projects like the Square Kilometre Array, the Extremely Large Telescope, and the Roman Space Telescope will observe billions of galaxies across cosmic time. These surveys will search for spatial variations in fundamental constants, anomalous patterns in cosmic structure, and other signatures that might indicate multiverse effects. Advanced statistical techniques and machine learning algorithms will be essential for extracting subtle signals from vast datasets. The continued study of the cosmic microwave background will push toward ever greater sensitivity and resolution. Future missions might detect the polarization signatures of primordial gravitational waves, providing smoking gun evidence for cosmic inflation and its potential multiverse implications. Particle physics experiments will continue pushing toward higher energies and greater precision, searching for evidence of supersymmetry, extra dimensions, and other physics beyond the standard model. The discovery of new particles or forces could provide crucial clues about the fundamental structure of reality and its possible multiverse extensions. Future collider experiments might reach energy scales where the effects of extra dimensions become observable, revealing the higher dimensional structure predicted by string theory and other multiverse scenarios. These experiments could detect missing energy signatures indicating particles escaping into hidden dimensions. The development of more sensitive dark matter detection experiments might reveal interactions between our universe and parallel branes or hidden sectors. If dark matter arises from physics related to extra dimensions or multiverse structure, these experiments could provide the first direct evidence for parallel realities. Theoretical physics continues to develop new mathematical frameworks for understanding multiverse scenarios. Advances in string theory, quantum gravity, and cosmology are revealing deeper connections between different multiverse proposals and providing new avenues for making testable predictions. The study of holographic principles and emergent spacetime is revealing new ways that parallel universes might be related to our own. These developments suggest that what we consider separate realities might actually be different descriptions of the same underlying quantum information structure. Machine learning and artificial intelligence are becoming increasingly important tools for exploring the vast landscape of possible universes predicted by string theory and other multiverse scenarios. These computational approaches can identify patterns and correlations in theoretical landscapes too complex for human analysis. The development of quantum machine learning algorithms might provide new ways to process and analyze the exponentially large amounts of information contained in quantum systems. These tools could reveal new insights into the structure of quantum mechanics and its multiverse implications. Philosophical and conceptual work continues to refine our understanding of what multiverse theories actually claim and how they should be interpreted. This work is essential for ensuring that scientific progress is guided by clear thinking about the meaning and implications of these radical theories. The interface between physics and philosophy is becoming increasingly important as theories push beyond the boundaries of direct observation. Careful conceptual analysis helps distinguish between meaningful scientific hypotheses and mere mathematical speculation. The potential for experimental verification of multiverse theories depends critically on continued technological advancement and theoretical innovation. While parallel universes might seem permanently beyond the reach of observation, the history of science suggests that today's unobservable phenomena often become tomorrow's experimental facts. The development of new experimental techniques and more sensitive instruments continues to expand the boundaries of the observable universe. What seemed impossible to detect just decades ago now forms the routine subject of laboratory experiments and astronomical observations. International collaboration will be essential for tackling the enormous technical and financial challenges involved in testing multiverse theories. The scale and complexity of the required experiments and observations exceed the capabilities of any single nation or institution. The future of multiverse research will likely involve increasingly close collaboration between theorists and experimentalists, with new theoretical insights guiding the development of experimental tests and observational discoveries inspiring new theoretical frameworks. Educational and outreach efforts will play crucial roles in preparing the next generation of researchers and maintaining public support for fundamental research. The concepts involved in multiverse theories challenge traditional ways of thinking about reality and require new approaches to science education and communication. The implications of multiverse research extend far beyond physics itself, touching on fundamental questions about the nature of existence, consciousness, and meaning. As these theories continue to develop, they will likely have profound impacts on philosophy, theology, and our understanding of humanity's place in the cosmos. The quest to understand parallel universes represents one of the most ambitious undertakings in the history of human thought. Whether these investigations will